Okay, I guess I'll just get started here. Give me just 1 second here. I'm going to go live. Hey everyone, welcome to another Common Lisp study group. And it sounds like we have some feedback issues here.
More feedback. Just a second, Rum. Pavel, I think we heard you. More feedback. Pavel, I think we heard you.
Hey Pavel, could you try saying a few things?
I saw his avatar, pulse.
Could have been anything, to be honest. Hopefully we get this resolved soon enough. I think we actually have people watching now.
Yep. My apologies. We are having a few technical difficulties right now, so...
I'm one of them. But
we did get some output from you, Pavel, but I don't think we, heard anything. All right.
I guess today we'll be continuing our Concurrency in Common Lisp series. We have with us the author of CLAflow, Pavel Korolev, who will be hopefully when... I apologize if I mispronounce your last name, Pavel, but he is the author of CLAflow, a very nice library that we mentioned at the end of last week's stream. We'll come to showing off his library. He's having a bit of some technical difficulties with his microphone at the moment. But in the meantime, Elijah is going to be continuing his discussion on some concurrency libraries, beginning with cl-async. So Elijah, without further ado.
hello again, everyone. Can everyone hear me just fine?
Yep.
Cool. Awesome. So yeah, we're going to be discussing cl-async, or at least I'm going to be covering cl-async and possibly a touch of some promise stuff and some of that, area. Let me go ahead and get over to my code here.
Can you share your screen, please?
Oh yeah, oh yes, yes. You actually have to share the screen so that you guys can see anything. Yes, share the screen. Yes, that would help. Anyway, there we go. 1 second. Go over there. There we go. And hide that. Okay, so, and I will increase the size of my text in a moment. I just want to get my stuff up. Dropbox, junk, 9.6. Threading, I think, is where I left it all. Yes, cool.
Font size, but...
Yep. Zoom frame in.
Well, I can read it fine, but yeah.
How about that? That better?
Yes, much better for my end.
Okay, cool. Okay. Just pull in all of my stuff here. Oh, that's fun. Really? That's amusing. Just gonna pretend that I didn't see an error there and hope that it doesn't. It's going to break on me in a moment
this week, huh?
It's been... yeah, sometimes...
It loaded just fine that time. God, that's weird. Okay, so load all of this in. Let's just hope nothing broke. I'll know soon, trust me. I think I have. There we are.
Yeah, I mean, if libuv isn't working, we got problems.
Yeah. There we go. Cool. So, cl-async. CL-async is a library for doing single-threaded concurrency, as opposed to the multi-threaded or parallelism style concurrency we were talking about last week. And I guess, just to sort of make a point of it, the definitions at least that I use, and I think candidly, most people use for parallelism and concurrency here, are that parallelism is when you have multiple cores working on a task, whereas concurrency is when you're working on multiple tasks at once. Concurrency is when we're working on multiple tasks at once, right? And so what that means is you could definitely have situations where you have a single task that you're using multiple processors to work on. Say a graphics card is a sort of a classic example of this. You've got thousands of cores all working on trying to put pixels on your screen. Or you can have cases like with cl-async here, where you're only doing a single thread, but you're juggling multiple tasks, on that single thread, without any one of them blocking the progress of the others for any significant period of time. And of course, as we were just showing last week with L-parallel, is where you have multiple processing threads and multiple tasks you're operating on, and that's where you kind of get this sort of intermingling of parallelism and concurrency. And it's always a little bit fuzzier than that. The general idea is that parallelism is about having multiple working processing, having multiple processors, whereas concurrency is about having multiple tasks to operate on. And cl-async is about, juggling multiple tasks. And it's not really alone in that. It's like just about any other sort of really event-driven, event loop sort of framework. It's about, you've got a whole bunch of things that are happening, and you need to deal with them somehow. And you need to make sure that your handling of any one of them doesn't prevent you from handling the others, for any particularly significant period, even if you only have one thread to operate on. So the basic, sort of system with cl-async is you have this with event loop operation here. Really, do I seriously not have company enabled in my REPL? That would be amusing. I did not have company enabled in my REPL. On. With event. So this with event loop form here is sort of the very basic operation in cl-async. Most of the API, I'd say just about all of it, will completely blow up in your face if you try and make use of it.
Sorry.
Hey,
You
Pablo.
can hear me now, I guess. Hello.
Hello. Awesome.
Finally.
Yes. Well, I can sort of shelve this for a while if you want to talk about flow for a bit.
No. You probably should continue.
Okay. I mean, either way, I've only just really gotten into it, so if we wanna pause it for your stuff,
Pablo, it's pretty late out there. I'd rather just have you, go ahead and,
Oh?
just go ahead.
Yep.
We're gonna, just switch up a bit, switch to CLFlow, and then get back to cl-async.
Yeah, okay.
If you could share your screen, that would be excellent.
Yeah. Just a moment, I guess. Let's see what I have here. My REPL. Let me just... Okay, share. Where is it? Option. Okay. And... entire screen. Okay, that should do, I guess.
There you go.
Okay, so I can doodle, I guess. Let me check. Can I doodle it? Okay.
Oh, wow. Okay, nice.
Can you do doodles? Okay, so that will be much easier to explain with doodling on the screen. Let's see. Okay, so CLAflow. It's quite easy thing, and but the idea behind the CLAflow is quite simple. It splits execution into two parts. One part is actual execution, so you have a dispatcher thing that accepts flows, and the flow thing that describes the execution. That's not a really helpful explanation, but let me just draw a bit. So let's assume that the circles are a unit of execution, like any source code here. This goes into this circles. And we can describe parallel execution like having the entry point, then we go into different different code blocks that executed together in parallel, and then they return some results which we need to process or whatever. And CLAflow helps you to describe those flows. I call them flow, whatever. And also I use crappy shorthand syntax series already. Okay, so you describe this flow and pass it to the dispatcher that runs it, basically. More on that later. I guess I'll just... Can you hear me all right, by the way, or understand me at all?
No, absolutely. We can understand you.
Oh,
I do have a question, though. So are you saying that CLAflow kind of like allows you to build like a pipeline then, like of different functions that can run in a...
No. It, like, you can have a lot of blocks of code. I call them atomic blocks.
Okay.
Which are which can be run, basically. So I'll just write one, basically, in my REPL. So it looks like something like atomically. And now I can do any computation here inside this block. The atomically block in Flow is a unit of execution. So I can do whatever here, like log. I don't have this one. Let's just load it. Quickload. What's that? Log first, yeah. What?
Oh, you typed in...
yeah. Sorry, Quickload. And I just let me... and I don't know, hi. It won't do anything right now because once I hit enter, because I need to run it through an executor, but whatever. Whatever this prints, we don't care right now. By the way, what's that? Whatever. If we run this, we need to have a dispatcher first to run the blocks, the code of blocks. Blocks of code, actually. Blocks of code, sorry. And it basically you need your own dispatcher because only you know how to run those blocks. And I have a simple system. If you don't need any complex dispatching, you can use simple flow dispatcher. I think it's called dispatcher. See, yeah. So I just for dispatcher, I'll explain what dispatcher does in a couple of minutes, I guess. Dispatcher, simple flow dispatcher is make what's alright. That's a dispatcher. Okay, cool. So dispatcher is just a function that accepts, we can actually go flow run. The dispatcher here is the function that has two arguments and any keyword, two main, or how it's called, primary arguments, and any number of key arguments. We then pass this dispatcher to flow run, which starts executing our flows. So it's dispatcher here, and flow, I'm not sure why there was an error there. Atomically, small pi. Wait, sorry. No, that's an error. Why? I just forgot the syntax. Oh, right, because that was quite hard. I have an engine called CLBudge, and I wrapped flow there, and it has a bit different syntax, so that's why. Okay, so what we did here, we run the flow block, which is called atomically, through the dispatcher. This atomical block is actually is this circle here. So we can have all right. So we can arrange those atomic blocks in different configurations. We can say, for example, let's run them serially, one by one. This is basically what you do by default, running blocks in serially. So we can say, it's not very exciting, but we go like from the basics. We can say flow serially and print 2 blocks hi there. 2 blocks serially, one after another. Here we go. And not very exciting. So now next step, we're going to the next step, running blocks in parallel. So going.
I have a question. In the serial block, could you pass data from one block to the next? Okay.
Yeah, you can basically, the last value of the block is passed to another.
Okay.
Passed to another. So we can pass actually there and have it here, arg and arg. Yeah, here we go. Well, that's okay. Let's do this way.
Okay.
Here we go. So we can pass values. We can actually pass return a list. Either world, I don't know, world, and structure it in the argument definition, parameter definition of the next block. So their world, whatever. Their world. Here we go. So it's very convenient. Okay, so now let's dispatch those blocks concurrently, which is quite exciting. So there is another primitive is concurrently, which tells us that following blocks are going to be executed in parallel without any blocking. So what should happen next is our blocks theoretically. We can't be sure in which we can do it here. In which what will be the sequence? No, what will be the order of them? We can't be sure. Okay, so we do there. Let's see what will happen. Okay, one more. No, that's not very exciting. Let's do this way. Let's put sleep here. Let's put sleep here. Wait, whoa. Sleep. So what should happen? We should sleep for a while for this first block. For this, let me do it. First block. Oh wow, exciting. We should sleep it here. So our there log. What was it? Line should print it first, and then hi should go after a bit of seconds with us here. Let's do it 2 seconds and clean up our screen. So hopefully that happens. No, that didn't happen because why? That's quite wrong. Maybe dispatcher is single-threaded. Let me see. You can pass number of threads. No, it's 2 threads. Let's pass, I don't know, 4 threads. No. Why? Oh, no, that's wrong.
Hey, Pavel, I don't think you changed the threads there because it's a def var.
Oh, yes, sure. But, yeah, true. But actually, that still should work because yeah, that's wrong. That's not what I wanted to show you, basically. All right. Well, strange.
So are you consistently getting?
No. 1 second. Just let me test it a bit. Maybe I'm just not sure where the sleep is going. There. Okay, that works in not concurrently actually. Because why?
Well, why don't you put different timings? You know, make one 5 seconds, the other one 2.
No,
it shouldn't matter. But you know, I know it shouldn't matter, but I just kind of am curious if it's really going to.
No. It won't work for some reason. I'm not sure at the moment. Yeah, this works. Well, we actually shouldn't wait. We can't be sure.
No.
All right. Basically, in this scenario, it should print hi there since 1 second.
Right. It depends on which one finishes first, but that's what concurrently.
I'm just wondering what I'm doing wrong. Okay, so if I run tests, 5 a.m. run CLAflow tests. Oh wait, CLAflow tests. Maybe this? No. Okay, we're going deeper. I thought that will be much easier, but I guess much quicker. Project, CLAflow, tests. What is that? Suit. I didn't know it. Quickload, I should have. 5 a.m. Run. That's quite strange. What's happening here?
Do you need this?
Like this. Restart. Tests. Yes, it loves this. It's very strange. CLAflow. Alright, this is kind of weird. Okay. 5 a.m. Run. Okay, so it's broken. That's very sad. Alright, let me just go back a bit and this history of it. It might be broken since maybe last. Yeah, I did some changes. Let's go just a bit back. I should probably have checked it before going to stream. So I'm sorry.
It's all right. This is kind of normal for the stream and live streaming in general, so don't feel bad.
Okay. Don't feel bad at all. We have multiple episodes where
things go left.
Yes.
Okay, now it works. Okay, I hope the test suite is okay. So what did we do?
Just before you continue, just a question. This is not something that I'm assuming that this is like new code. It's like if people download the Quickload one that's on QuickLisp, will be fine. Like, or is this just in your?
Let's see. Okay, so this uses a custom QuickLisp distribution called Bodge.
Okay.
And I don't think main QuickLisp distribution has the recent version.
Okay.
Recent enough version.
Got it.
I can probably put it there, but I'm not sure when Zach will put it actually into the list.
Oh no, that's fine. I just wanted to know, like, if people started using it from the main distro, like, what kind of, like, like features might be missing, or in general the API.
It's better if you want to start using it. It's better to install a custom distribution.
Okay. And if you can, like, send me the link, I guess, to your custom distro, or
yeah, sure.
Then we could try it out, or I could even post it on, like, the YouTube channel for people to play around with it. Give you thoughts.
Okay, let's see. Where should I?
If you're on Discord, or if you can send it to Michael, he can send it to me, and we could go from there.
Just,
all right.
Just IRC it to me, and I'll forward it.
Should I do it right now, or maybe?
No, later. You can do it.
You can do it later.
You can do it later.
Okay. Okay, let's see if that works now. We need a dispatcher. Different. Okay, we have a dispatcher now. Let's dispatch it. Where is our flow? Yeah, okay. No, okay, because we don't have a log for CL. No, that's still wrong, unfortunately. And I don't know why.
Remove the first sleep there. It just could be that they both finish at the correct time.
Oh, that's the point of.
Yeah, it's still running it serially, even though.
Yeah. Let's try shorthand. That's not it.
I think it was.
That's still serially.
According to your documentation, it says it returns a list of block results in the same order they were specified. So maybe it's working.
Yeah, but I mean, it could just collect them in the right order. It doesn't need to execute.
Yeah.
Right.
I think maybe I'm doing something weird here.
Is it possible that your simple dispatcher actually has a bug such that it's not actually dispatching to multiple threads?
That's quite unlikely. Otherwise,
it is, a simple dispatcher.
yes, but it's not that simple. Okay. I wonder.
Well, it's clearly dispatching.
All right. I know why. Sorry, I know why. That should be. I fixed that. Let's see, because probably this. Let's see. Okay.
Yes, there we go.
So the second argument, atomically blocked, is invariant. What does this mean? When we access the same resource from the different threads, we don't want to not only access but write into some resource. We don't want several threads to write into it at once. So we can define, like, set invariants, which will tell our dispatcher if we want this atomical block to have like pseudo mutex. It's not actual mutex, but if we set here, I don't know, what's read only. Let's say it's just, I don't know, invariant. That would mean that this atomical block won't be run in parallel with any other atomical block with the same invariant. Does it make sense what I'm saying?
Yes.
Yes,
okay.
That's correct.
Yeah, and the invariant was nil for both of them before. So
Yes, exactly. Okay. And nil is I not quite remember exactly. No, yeah, that's why basically.
So basically, you created like a shared variable between those two.
Yes,
okay, got it. All right.
They were both classified the same way, so they won't run in parallel.
Yes.
Yeah, so they were run in serially, which actually makes sense now. Okay. So, all right. Those are basic blocks of CLAflow. Doodling enabled. Sequential flow. All right. Atomic block, sequential flow or serial flow, and concurrent flow. Now, how to collect results from concurrent block? When blocks are run serially, it's quite easy. We just grab the result from the previous block. Okay. Result. Print high. Okay. If we run blocks concurrently, we can't do this because concurrently we don't know when the results arrive. We should wait till all the computations inside concurrently flow are finished. Then we can get the actual results from all of the flows inside concurrently flow serially. Just structure it right away. Like we have a result here, hi there. arg1, arg0, arg1, and log info. Or actually, we can just do this. That will show what actually we are receiving value. What? R? Okay, that's here. And we see that we received. That's not very interesting, not very exciting. Let's just do some sleeps inside this sleep. Okay. So what's happening? We are. Let's just do a bit of. Wait. Oh, is that? That's wrong. That's wrong indentation. Oh, I see. Okay. That's correct indentation. Can you see how it's actually two flows here in serial block?
Yes.
And yes, okay, it's one.
Well, yeah, and then the atomically is the next one. Yeah.
Yeah. Okay. So what happens when concurrently block runs everything inside it and collects that into a list, that which then goes into the next block in serial flow, which is our value, and we print it. Okay. So there are another primitives in the CLAflow. Should I go into them, or is that good enough? Okay, I maybe explain why I came up with this thing at all.
Okay.
Sure. Okay, so I tried different approaches. First of all, I wanted asynchronous execution, and I tried cl-async, and I tried green threads, and I tried cl-cont, which is continuations in Common Lisp. Very exciting at first. But I actually needed to run certain code in certain threads, and I couldn't do that with all of those leaves. For example, when you are working with graphics or UI, often you can't work from different threads. So the context of those things are bound to a certain thread, and you want to execute a code in that thread. Sometimes you can rebound or rebind the context to the thread you need, but that's quite slow. Or not, it depends. So separating actual execution and definition of the computation tree, let's call it computation tree. Now I can run logs in the threads I need, because I actually can pass arguments to the dispatcher via atomical block. So I can actually say whatever here. The simple dispatcher will ignore it, but you can write your own dispatcher with that will accept this atomic block, and you will it will see those arguments, and it can act on them, whatever, like in the manner you want. So this will work, it just will be ignored. Okay. And I wanted to pass values between threads too. So when I do, for example, when I'm starting an engine, multi-threaded engine, I have a graphics thread, I have an audio thread, I have AI thread, and I need all those systems initialized. Using those flows, I can write something like maybe even concurrently, just like this atomic block in its, I don't know, graphics, and say system graphics, for example, graphics. Graphics. And the system AI, I don't know, AI, init AI. And now, if those systems are confined into the thread, which is a simple way to write concurrent code, basically. You can confine all your state into the one thread, so only this thread can modify the state. That would guarantee that I initialize graphics first, then I go into AI, then I can actually go into initialize UI. I can't initialize UI before graphics, and this will guarantee that the order. That won't. Sorry, but this will serially. This will ensure that the order of initialization is like this. Okay. I can go now into other parts of field flow with.
I have a quick question. For the concurrency stuff, could you, because, as you rightfully mentioned on your, on your documentation and stuff, there's no defined memory model. Did you have to design kind of some of the semantics behind how you deal with volatile variables and things that are being passed between the different threads, or how did you handle some of that? If I'm writing an application for it too.
That's an interesting question. I never stumbled upon issues yet.
Okay.
Basically, but I'm not sure, but maybe. Well, all right. There is a point in execution when the runtime ensures that all the values that were previously written are flushed. These operations are flushed. And access to the atomic variables is actually one of those points. And because CLAflow uses those atomic operations, that should ensure that any volatile memory should be flushed, basically. I never checked.
Okay.
But that should work.
All right. Cool. Thank you.
Yeah. All right. So, all right. Let's quickly cover other CLAflow API, I guess. So what we have there, we have repeatedly, dynamically, asynchronously. Okay. That's a weird name, maybe. Okay, let's start with dynamically. So we can, sometimes we want to inject another flow, or we are not certain what to run in the flow at the time of writing the flow definition, the flow descriptor, whatever name. Let's do this actually. Define run. What's that? That's not common Lisp. Define run flow. Flow run dispatcher. Flow. Now we can just run. Can we actually? No. Can anymore? Or can we? Whatever. Run. What? Oh, okay, because we don't have this. Let's return our atomic logs here. Log hide for hide. That will be ignored anyway. Nothing like there. Sometimes we want to inject the flow within another flow at runtime. For example, when we're defining flow, they're defined at whatever the time, the design time, compile time maybe. What? Yeah, that's weird because wait. What now? I probably shouldn't define this wrong. I don't know. Oh, Jesus. Jesus. Now it won't run for the reason I don't know.
Don't you have to put, if you're using serially, do you have to put nil? Like...
No. The only thing that accepts invariants and arguments to the dispatcher is the atomic box.
Okay, got it.
So all code is actually all code that should run during flow execution is inside atomic blocks. There is exception in dynamic flow, which as I explain right now, if I just make those run again. Let's do this. I'm not sure what I did, but I did something bad. So flow, log for CL, what else there? Simple dispatcher, simple dispatcher flow. Okay, def parameter dispatcher, run our flow. Serially. Okay, here we go. sometimes we want to. Okay, so this flow is like constant flow. Whenever we run it, we can actually put it into a parameter. I don't know, definer flow, and run it like flow run dispatcher flow, and we run it. And we can't change it now. This flow is like forever in this configuration. But sometimes we want different behavior depending on some state. Let's just write another flow which explains how to use dynamically. Thank you, Sly. That's not here. Now, dynamically accepts the. Okay. Let's define another parameter. State. I don't know. State 0. And if we I don't know, when state, not if, state 0, let's go with this flow. So we can generate flows dynamically this way. Hi. All right. So in this case, it will write hi if the state run on 0 and sorry, state equal 0. That was Russian. Sorry. Or it will it will print hi there if the state isn't 0. Okay, that's this flow. Let's run it. Okay, so we have hi because state is 0. Let's define state non-0. 1. Alright, now we have hi there. Another primitive is asynchronously. Now this code log allows you to interface with other asynchronous code. Basically, in its body it defines two functions that called continue flow function and interrupt flow, which can be called from any other code. Maybe you have a cl-async, for example, for some reason, and you can dispatch or I don't know, put any lambda into cl-async, and it will invoke it at some other time. For example, asynchronous I/O. For example, when you receive the frame, but you want to continue flowing with CLFlow, you just call continue flow function, and it will continue flowing. Let's do it this tricky way. For example, the parameter, that will be continuation, actually. Continuation. Now, continuation, whatever bad naming. We just flow asynchronously, and we just set up that's true continuation, basically. This way, continuation, and we just continue flow function. Oh, and we can even pass arguments here. Flow atomically 3 or whatever, arg high log of high info or whatever we pass here, arg. Let's see. So we run our flow, run flow, and we just printed hi from Let's just doodle a bit. Doodle. We print this high. And we saved our function that we can invoke to continue flow execution into continuation, variable. So if we call this function now from the continuation, it should continue running this flow, and we can print anything here, basically. Continue flow accepts an argument. And this argument will be passed to the next flow block. So let's do this. Call continuation. And I don't know, there. And here we go. We just continue reading whatever we want. Hi, hello, I don't know. You got the idea. So it's like continuations without CL count. And another, maybe last thing, is the repeated flow. I added it quite recently. Is it here? No, it's not even here yet. No, it's here. Now, sometimes you want to have a loop, and having a loop, we can have a loop with all the primitives we have before, but there is one little problem. It will consume our stack, execution stack, because every atomical block is actually a function, defined as a function, and it calls a next function and next function, which are blocks, atomic blocks, and repeatedly have all the machinery to not eat through our stack. It unwinds the stack when needed. Okay, so let's do what? Let's have a variable called iterator. Index, maybe index 0. Now we can flow repeatedly while our index, I don't know, less than 3. Let it be that. Let those be nil for now. And we just incaf index. Oh, we can reset this index after serially. Then we repeatedly execute those blocks, and then we just reset our index. And then we reset it. Set index 0. Okay, that should work. Yeah, certainly set F. Oh, that's wrong. Okay. Did I just broke it again?
Well, you aren't running it, and also I think it was right the other way.
Oh yeah. Sorry, I've just defined the flow. I didn't run it yet. Thank you. Let's run it.
I think the test was right the other way. I'm not certain though.
That should be end test form.
I think you want less than index 3.
Oh no, no. Actually, yeah, end test, yeah. Yeah, so it when it's true, you stop iterating.
Yeah.
Oh,
Yeah,
I see.
should do that. Unless I lied with the variable name. Let's see. Nothing happened.
Hooray.
Then alright. Let's see if this works. Okay. Hi there. Why? That means I lied. I need to fix that. Hi there. Let's see. Repeatedly. Oh, alright. And test form. That's quite bad. Okay. Run flow. So what happened here? We run this flow 3 times. Well, this flow basically. In loop. What that means, for example, in game engine, you would have a game loop, and that's it. And sometimes you want to inject some other flow into it, and using this repeated flow, I can have a synchronous loop. How can I better explain this? So I can have a dynamic flow here. I want dynamic flow here. Dynamic flow. With whatever code. And I can inject flow here, any kind of flow. And it will be run. It will be run. During this iteration, and
pretty nice way to do like an event loop. Yeah.
Yeah.
I like
yes,
that.
basically. Yes, exactly. What else should I say about it? What else do I have here? Asynchronously. Well, that's basically it. That's those. Let's see. Oh, that's. What's the API? And I have this stupid shorthand syntax you saw that confuses Clojure users, basically. Yep, that's it.
So
that took much more than 10 minutes. I'm sorry.
No, that's fine.
I think we had a question.
Oh yeah, you're good. It was interesting.
Yeah, it's very interesting. I have a question though, regarding what was it? I think it was asynchronous flows. Like when you get the continuation, could you pass that to other flow objects that are in your flow? Like if in case that you're running, let's say like a concurrent flow, and based on a state of a particular variable, you'd want to pass a continuation to the next, block. Like, is there a way to like?
You can pass this function, but that won't do anything I explained. For example, if I understood correctly, so we have a asynchronous flow,
right?
And we can pass whatever. We can pass this continue flow function, which is actually a continuation function.
Okay.
To the serial, for example. What's that? Atomically. Cont. And we can kind of uncall cont. Is that the case you were describing?
Yeah, I was describing that, but I was describing it like in the situation that when you use interrupt flow. Like, let's say that you had a state inside your flow function that you wanted to interrupt, but you wanted to grab it and then continue that. Does that mean you interrupt and then you return continue flow to the next block? Like
no, to interrupt flow actually stops flow execution at all, like
completely.
Halts it. Completely, yeah, because that.
Okay.
You should call interrupt flow when there is no way to continue flowing.
Okay, got it.
Throw some error. If you want to go to the next block, you should call continue flow. You can, call continue flow with a list of first argument will be state, and the second argument will be error if you encounter it. And atomic clock, you just...
I might be mixing my understanding of what interrupt was, because I was thinking like an interrupt, like if you're like reading a file in like an operating system, you do an interrupt, right, with a callback function, and it reads in the file and then comes back, says, hey, here's a file descriptor, right, behind the scenes. I was thinking that interrupt flow was giving you that kind of functionality. So
I see. Yeah. No, it's actually continue flow, basically.
Okay, got it.
So you I don't know if there's any function like receive frame, which is an asynchronous I/O function from whatever library, imaginary library, and you have a it accepts because it's asynchronous, it accepts lamp callback, so callback with our frame, for example, and then we can call
continue flow.
We can call continue flow with that frame.
Got it. Okay.
That's
okay. That was a situation.
What I'm doing some things. Frame, and now here we can process the frame. That's just frame, basically.
Okay. Cool.
So right. that will from here from.
And in principle, you could even have the frame processing happen on a particular other thread if that was necessary.
Yes, exactly. Yeah. So you can say like...
Nice.
That's really cool. That's really, really nice.
Yeah, I like it a lot.
I'll have to tinker with what you can get away with implementing dispatchers, because there's... I was thinking recently about implementing... a thread pool manager, not unlike Swift's new Grand Central Dispatch system. Well, it's not really new, but the Grand Central Dispatch system, which is basically it's thread pooling on steroids with lots of worker queue kind of stuff. And I was thinking recently, due to my own sort of frustrations with cl-async and a few other libraries, that I was going to, see how difficult it would be to try and implement all of the worker queue logic from that. And I'm thinking now, I wonder if it would be possible to implement a dispatcher for Flow that would be able to run atop something like that.
Sure. I mean, this dispatcher is just a function. I can write. I can write. Let's see. It should be easy. Define dispatcher. Dispatch it. Okay. So there's a task. Task is something that CLAflow does. That's most of the time it's atomic clock, and then an invariant so your dispatcher will be aware that it shouldn't run invariants at the same time, basically. And now we can have a key for system. We have a system. System. And allow other keys because reasons. And now we'll just print where we are dispatching at the moment. Dispatching in dispatch, and there should be your logic where you want to dispatch it, but not right now. System. And we just call task. So that's the dispatcher. That's all. It's a single-threaded dispatcher, basically. But it would work, I guess. No? Invariant. All right. Declare, ignore, fuck invariants. Sorry, that's invariant stream. So no more invariant. Because it's a single-threaded dispatcher, we don't need invariants, actually. There won't be any concurrency between whatever we write. So we can run our flow, any of our flows. Dispatch, flow, run, dispatch it serially. Let's just keep it simple. Log info, yo. Okay. I guess that yo one. Okay. can see this dispatch function called actually 2 times for each atomic block with the system being nil. But we can pass a system there. Okay. System, what's that? Worker pool. Worker 0, I don't know. Worker 0. And here we go. We're dispatching Yo and worker 0. So that's it. You can dispatch it in any way you like, in any environment.
That's really
cool. So the dispatcher function could close over whatever state is needed in order to actually send to the right.
Yeah, exactly. You can even define dynamic variables there, special variables there. So inside atomic block, you can have a needed,
I can totally see now this can be extended to dispatch anywhere, so you could make that Grand Central dispatch.
I do have one other question, which is how does the dynamically flow keep track of what dispatcher it needs to run on?
Oh, that's a good question.
I could just read through the code on that myself later if it's a really complicated explanation, but
yeah, the thing is the only thing that should I mentioned that earlier. The only block that can run your code in a certain way is atomic block. That's its whole purpose. So you can ensure that anything inside atomic block is run in a certain way. But none of the other code can be configured to run somewhere else. So what happens actually, that dynamic block runs the logic in whatever thread it happens. You can't control it except for you can actually accept arguments in the dynamic block. Dynamic.
Sure.
So you can pass here something. I don't know. Pass state there.
Right. Yeah.
Flow.
I mean, I guess my real question is so I'm assuming the dynamically block it's effectively an atomically block, but it processes the return value specially, right? The return value of the flow that gets processed.
No.
Okay.
It's not safe to assume that it is it's not an atomic block inside.
Sure. Right.
Kind of, but not.
Right. Okay. But the idea is the return value, you return a flow object.
Yes.
And it then dispatches the tasks of that flow object. Right.
Yeah. It's like injecting. It's like replacing this dynamic block with
whatever that returns. Yeah.
Yes. Exactly. Yes.
So, So the dispatching function doesn't need to return anything special, right?
Yep. No.
Okay.
Well, it should return the flow. It will be an error. Well, it can return nil. It basically can run nil block.
Oh, no. I mean, if I were to write a custom dispatcher, right?
Okay.
It's not required to return anything in particular, because it receives a task and it does something with it, but its return value isn't used for anything, right?
Dispatcher doesn't know anything about what it executes.
Right. Yeah. So okay. So how does the dynamically block know how to know what dispatcher it should be running on?
Yes, I saw. I mean, I understood the question, but there is no guarantee. There is no any guarantee where this code, in what dispatcher the code will be run. Well, I mean, it certainly will be run through dispatch it.
Right.
But
there's no guarantee where dispatch it will be run. My question is, how does it? I guess is flow run a macro?
Yes, that's a macro.
Okay. I'll have to read it, because I have a very fiddly question about the implementation, and I don't think it's.
Yeah, sure. We can expand it. It's not really. It's much prettier. It's much prettier than cl-cont, but still a bit ugly. Okay, that's the.
That's interesting. I see.
Okay, we can remove.
Oh, that's clever. That's really clever.
Good. Thank you.
I see. Nice. Okay, I got it.
So basically, those are functions.
Yeah. I get it. And they all know what their dispatcher is.
Yeah.
Yes.
Okay.
Yes.
I see now. Got it.
Okay.
So internally, it looked like you were almost like generating like. Did I miss? Could you show that expansion just one more time?
Yeah, sure. For dynamically
or for dynamically.
Okay. So here we go. And that's it. Yeah. Is that it? Yeah. That's the function. Now
okay,
this is the function.
I see. So you know that you're creating a new dispatcher there at the end. Okay, got it. Okay. All right.
Well, dispatcher is passed here, and the result callback, that's basically a callback to call the next function and the argument that is going into the block.
Okay. Yeah, and I'm noticing, and Elijah, this brings up one thing that I think we need to cover here, which is the function stuff. I'm seeing function signatures here that are being generated. For the
function types?
Yeah.
We need to finally have the type stream. We really do.
We do need to talk about the type stream.
Anyway.
This is another example of how flexible there are. That's awesome. This is really cool. Thank you for showing that.
Thank you.
Yeah, Pavel, this has been great. I mean, I tried to read your library and the documentation and try to get a gist for what it was doing, and I could not understand it. But this really helped a lot. And I actually suggest that, like, when this is put on YouTube, maybe you can stick this video in the README or something.
Yeah, sure, I would. I certainly would. I just need to draw some images to explain the thing. It's quite easier than writing the prose, actually.
Once we post this on, once this YouTube the stream is done, Pavel, we can I will send Michael, you can actually find the YouTube link in the channel automatically, and you could just send it to him so that he can link it on his site.
Yeah.
So
sure. I also I guess I can send him how to install the Bodge distribution to get the latest CLAflow.
Oh, that would be great, because I will immediately post it on the YouTube in the description so that folks can actually get the latest from your distro rather than getting it from trying to get the quick Lisp one.
Okay. Yeah. Sure. Mm-hmm. Thank you.
No problem.
Good time.
Thank you so much for showing us this great library. This is very interesting. It's giving me some ideas now to check out.
Yeah, definitely.
Yes, thank you. Any other questions from our audience? Maris or Richie? George? All right. Thank you so much, Pavel.
Thank you.
Yeah.
Yep. Thanks. Let's go back to.
Going to be a long stream if we pick up cl-async now. I'm up for it. But,
I'm fine with it if you guys are.
Okay.
Yeah. No complaints here. Go for it.
Cool. So let me share my screen again. Okay, so that was awesome, and now for a much less threading intensive library, to put it lightly. As I was starting to get into a little over an hour ago now, cl-async is a much more single-threaded concurrency oriented library with some nice stuff for networking in particular, and some basic event loop management. And so the basic operation, the basic sort of setup with cl-async is you have this with event loop macro. I mean, actually, you can. There's another way to do it. It's like start event loop, and that one you pass it a function, and it calls that function inside the now started event loop. But with event loop, just short circuits that if you just want to give a body of code. So we have this with event loop macro here, and then from inside of an event loop, you can call the various functions that cl-async provides, and then those generally will all schedule stuff to happen on the event loop as it's going, and pretty much exit immediately so that you can schedule more things to do. And then once you're done doing your thing, whatever's been scheduled on the event loop will start processing. And then once there's nothing left, holding the event loop active, it'll close down. So that's sort of the basic idea here. And so the most basic thing that you can do with it is you can make a delay. So I can delay here, and this takes a callback. But once again, for the really simple ones, there's with delay as well, which is just a bit easier. And I could say, hey, delay for 1 second, and then do that, right? And so it's going to sleep for a second and then do something, right? And this is sort of the basic idea here is that this delay block actually exited immediately, right? If I were to format, t bar here, bar, I could type, there, and somehow I got my parens unbalanced. See, bar prints immediately because this with delay actually, schedules that something needs to happen, and then it returns immediately, and then move on to the rest of what you're going on here in your event loop block. So you can basically just put pretty much arbitrary code inside of the with event loop, and most of the asynchronous functions will just sort of happen, and then you can move on to the next thing or whatever. So I've sort of got a couple of little bits of example code here that I was screwing around with last night to sort of demo different bits of the library. And I'm trying to decide if I want to go through this in the order that I come up with it, or if I want to go through it in the order that I found more interesting after having done some stuff. But this first bit here, delay n times for x, basically you give it in a number of times to execute, a number of seconds to wait between each time, and a function to call. It does a with delay, or so if n is greater than 0, does a with delay, then it does, calls your function, and then it delays for one fewer times, right? Pretty simple recursion there. And so I can say, here we are, with event loop, and I can say, delay n times, I don't have any of the code in this file compiled. I didn't, and apparently I didn't even have all of my dependencies loaded properly.
Excellent.
Wow, I'm being a bit of a scrub today. Live support.
Wait, you can actually...
What?
Well, I see a comment there. Like, are you pasting that into your REPL, or?
Yeah, I'm gonna paste that into my REPL.
Okay, good. I was just like, what?
I just sort of always do that. I always shove a comment at the top of my files that lists all of my dependencies.
Okay, cool. For a second there, I was like, you may have added. I was like, did you add support?
Wow, I managed to skip out on a lot of my dependencies. Wow, I'm feeling really silly. USocket. I'm not gonna demo USocket, but I use it in one of my later examples as the client of a little server I create. So USocket there, yeah, got that, all my dependencies. Now does the file load? Yes. Ignore all the warnings. I'll deal with those later. Okay, so now that I actually have the code that I need, delay n times for x, right? We're going to say delay 5 times for 2 seconds each, and we'll hold Serapium. and this is gonna, gonna print out foo every 2 seconds for 5 times. Good old 5-second wait there. But just to actually demonstrate that the library really is operating concurrently, I can do this. And actually, I have this code right here. It's my delay test. I'll just execute that here. Delay test. You'll notice that it does foo, and then it does bar. And they kind of go back and forth, because foo is doing it's doing 5 times every 2 seconds, and bar is doing for 3 times every 3 seconds. Right? And so you see here they get interleaved because it's executing concurrently on the cl-async event loop. I actually implemented the same thing using a similar operation in cl-async called with interval. And basically, with interval, it's a bit weird because it actually returns a callback you use to cancel the interval. The idea is that you give it the delay period, right? And then it just executes this body once every X seconds. And then it'll just keep doing that indefinitely until you either call, it gives you this callback object, basically. And you either can call that, or you can call remove interval with that. Either works. And basically, what I did here was I basically made it an interval, right? And I say, call the fun, decrement the n. If that's, less than or equal to 0, call the callback, which, is the thing that was returned from with interval, which cancels the interval after that. So once it hits, n times, it cancels. And then basically just the same code here. It's the interval n times, same interface, does foo and bar. Like an interval test, same idea. And then I did something a little trickier, which involves this library called Blackbird. And Blackbird is a promises library. It's actually a rather nice promises library. I heard that, Michael. Blackbird is actually a rather nice promises library. It's a pretty simple one, though, and it's got integration with cl-async. It was actually built to replace the promises code that was baked into cl-async before now, but now it's actually spun out as its own thing that you can integrate into other libraries if you wanted to. And it's pretty simple. You can say with promise and get a resolve and a reject, and basically the idea is that you set it up so that the resolve function will get called with some value that resolves the promise, or the reject function will get called with some error that cancels out the promise, and then the with promise macro returns the promise object that now you've set up to be resolved at some point in the future. And the idea here, delay n times for x with promise, the idea is that it will resolve this promise with a t after all of the iterations are complete, and that way I can actually say, hey, run both of these, and then I use Blackbird's let here, which basically it's let, but for promises. You give expressions that return promises here, and it will set it up so that as soon as all of those promises are resolved, their values will get captured in these variables, and then you can use them in this code body. And this all gets executed, asynchronously as well. This is itself defines yet another promise that gets resolved with whatever this code evaluates to. So this basically lets me wait until all of the, all of the printing is finished, and then I can print out something at the end, which is, a lot of code now to emulate what we were accomplishing with Flow very easily just not a few minutes ago. But, this is what directly interacting with promises does to you.
That might be just one of the longest function names I've ever seen.
Oh, well, yeah. I mean, if this were actually in a proper library where I had nice semantic names, these names would be a lot shorter, obviously.
Yeah.
But, I'm trying to be very descriptive with what I'm doing here.
Yeah, I hear you. I know why.
It's okay. It's okay, dude.
Yeah. And then I did the same thing here, but I actually added, and this is sort of the next thing we'll get into, is I added a signal handler, which is a Unix signal handler. It's sort of the next another thing you can do with cl-async, right, is you can actually set it up so that cl-async operations will get triggered if Unix signals get sent to your process. Basically, a whole lot of stuff in cl-async is about setting things up to happen on the event loop when events occur. And so what I did here was I set up a handler on SIGINT, right? And so I can actually now do delay promise test with interrupts, right? And this gets a little fun, but I kind of want to have it ready when I show it. Inferior Lisp. Here we are. I run this, and I come over here and I send an interrupt signal. You'll notice I get interrupt printed out in my REPL there.
Dang, that's awesome.
And that's because I've actually overridden the SIGINT handler inside of my event loop. I notice actually part of the reason why I did all of that promise sort of bending over backwards is you kind of have to free any signal handlers that you establish before the event loop itself will exit. The event loop will actually just stay alive, not doing anything, until you free your signal handler. The idea being that as long as that signal handler is active, it may actually just be sleeping, waiting for some, interrupt to come along, right? And so the event loop doesn't want to exit until you explicitly free the signal handler, which meant that I needed to be able to tell when all of my code up here was done. And so I needed to add in some promise nonsense, or at least that was the simplest way to do it. But yeah, so that lets me properly set up a signal handler, do some stuff, and then after that stuff is finished, free the signal handler so everything exits properly. And then we sort of get down to the next little bit here, which is where I bring out the big guns, and something that I discovered and found really amusing, which is that I can actually integrate Baggers' awesome little live support library into CL-async and get myself a REPL running inside the event loop. And it's actually really easy to do. So there's something you would want to do for testing. It's probably not something you would ever want to do in practice, but it's nice because it lets me call all of the functions in the CL-async API without having to spawn off an event loop just to run them, and then do the setup and the tear down of that and see the results. I can just actually have it, I can just call these functions now. So for those of you who've never used live support or don't really know what that is, live support basically is a wrapper around. I copied that little bit there. Live support is basically a wrapper around some internal stuff in both Slime and Sly, and in principle it could be extended to support other Lisps as well. And the idea is that you can call this setup Lisp REPL function here, and that basically prepares Sly in particular. Actually, on Slime it doesn't do anything. This is something we added just for Sly. But it sets everything up so that you can basically run a REPL inside your REPL, kind of. And then the other thing is that you regularly need to call this update REPL link function, and this is where basically all of the Sly stuff is going to be run during the update REPL link step. And so when you run code on the REPL, it'll actually be executed by this update REPL link function in whatever bit of thing you've got going on. And so what I'm doing here is I'm basically creating an event loop that prepares a Lisp REPL, and then every half a second, notice I set that up. Every half a second, it updates the REPL. And now I have just a regular REPL, and I can do stuff on that. Ta-da! And you'll notice if I hit enter, there's a little bit like weird latency on there, and that's just because once again, update REPL link is only being called every half second. But that's fast enough for most uses. And now I can actually just use the CL-async functions. I can spin off stuff to run in the background, and this is all running on a single thread. So I could, for example, with delay. Say I want in 3 seconds, I want you to sleep for 10 seconds, right? And this is just going to demonstrate that this is all running on one thread. In a moment or so, oh, there it is. It's now running the thing that I delayed there. Now it's sleeping for 10 seconds, and now my REPL's not going to respond again until that delay finishes doing its processing. And there we go, and finish, and then it finished doing my REPL step. So this is all happening concurrently, but I can fire off CL-async stuff to happen in the background. This is a nice little test bed. So then we get some of the more complicated things that you can do. You can do, for example, you can do DNS lookups with CL-async. So I can say, hey, what's the web address of google.com? And what you'll get back is you have to give it a callback, like just about everything else in this library. And what you get back is basically the host and the kind of record that you got back. So if I run that, then I kind of wait for a moment. There it was. It got back to me eventually. This is all happening asynchronously, of course. This 2 here is because it's an IF, or is it INET? Yeah, it's IF INET. Yeah, there we are. Good old C constants. But basically that's telling you that this is not an IPv6 address, it's an IPv4 address.
Right.
But you get that back. So you can do VNS lookups, you can connect to servers. So you can do socket connect, yeah. No, was it socket connect? It was TCP connect, that's the one. And then basically you do, I could say, well, trying to connect to Google would require that I come up with an actual HTTP header, and I don't want to do that right now. But the idea is that I can make a TCP connection there, and I can actually spin up a little server elsewhere if you want me to demonstrate that. But I'm going to actually spin up the other side of this. I'm actually going to launch a socket server in a moment. And the idea is that I could basically, I can connect to a server. I can then write stuff on the socket and get a callback whenever stuff gets sent back to me. Actually, let me think. Could I google.com on port 80, and my read callback is going to be sop format t tilde a able octets to string underscore. No, I want to do it underscore 2. Yeah, let's try that. And then I'll really have some fun. And I can do socket. Was it write socket? Write socket data. There we are. What are you doing? Socket data. Yeah. And the idea here is that I can say, give me, that socket. And I'm going to do enable string 2 octets and say, let's see, do I have? Yeah, I'm just going to trust that Babel knows what it's doing for this. I want to do a get on slash. No. Oh dear. I have to remember the proper way to do an HTTP request.
It's HTTP. There's a URL, and then you have to say
HTTP.
get. Then you have to say the URL. No, you say get, and then the URL, and then yeah.
That?
Yeah, that's right. That looks right.
Yeah. Did I get anything back from them? I don't think I got anything back from them. I don't think Google's listening to me.
I'm sure Google isn't listening to you.
I probably could set an event callback on here and and now if I write to that socket, and no, I'm just not getting anything. That's amusing. Huh. I wonder why. Well, I haven't done any TCP connections in a little while with this library, so I can't really demonstrate that one. The side that I actually would prefer to demonstrate is running a TCP server, because that's much simpler. So what you do there is you say TCP server. You give a IP that you control.
Just a little note. Maybe it's printing in a thread. Where is the?
No, this is all happening on this thread.
Oh, all right. Okay.
Yeah, no, like this is all happening on this thread. CL-async is a completely single-threaded library, and I'm just cheating right now by having CL-async pump the events for my REPL.
All right. I mean, okay.
So, no, it's all happening on this thread. I guarantee that. I mean, I can actually prove that in a moment. I mean, that's like what I was doing up here, right? That's why that gets printed out properly. I mean, I could check my inferior list, but I'm going to use the same trick that I used last week, which is I'm going to create another thread, second thread. There we are. Now I have a second thread. Second thread. And then I wrote a really quick little socket client over here, which is just usocket. I connect to localhost at 8088, and then it gets the stream from the socket, and then it just makes a really, really dumb little console for me here. Oh, wow, right, because it doesn't, not directory, set package. To threading examples. There we go, cool. And so now I can say foo, and it just sends it back to me. And actually, I can now prove that this is actually doing its job. Format. Part of me wants to just pull in log4cl right now. I haven't tinkered with it in a while, but you know, it looked nice. It gets printed out over here. So the handler is being called on the right thread, and this is actually the same thread as my REPL here. So if I were to, you know, sleep for, oh look at that, I got an EOF back from that socket talking to Google. Just took a while.
That took a long time.
Oh yeah, no, I don't really know why that took as long as it did, but apparently Google takes a while to give up on its connections to you. There's probably some flushing thing or some like new line thing. Like I wouldn't be surprised if it's because Babel didn't properly translate the new line in my string, or some stupid nonsense like that, or maybe it just really was a malformed HTTP header. Hard to say. Oh no, I know what it was. I actually know what it was. I know this. You need 2 new lines. I always forget that.
Oh, that's right.
You're gonna.
Oh, you need to change the V20.
Oh, you're right, I do.
No, that's a malformed. I think it's malformed. That's the reason why. It's a malformed request. Do get/h. Yeah, I'm just looking it up. You were right. The first
thing is the get, and then
get.
it's the slash, and then it's HTTP 1.1.
Yeah,
right?
slash 1.1.
Oh, slash. Yeah, there we are. Slash 1.1.
Yes.
Okay.
There
we go.
That's it.
Cool.
It's just that the.
And you were right.
Yeah, there we go. Okay.
Invalid character there.
Oh well, yeah, that happens sometimes. I've encountered that before, trying to get stuff back from Google. They give you data that's not actually UTF-8 for some reason. Probably some binary payload they got in the middle there somewhere. Then I'm blindly doing an octets to string on that whole payload, so hey, who knows what I'm getting. But yeah, so there we go. Knew it would be a problem with HTTP. It's always the problem with HTTP. But yeah, so here's so I just pulled in from Google. You'll notice, as a side note, that I've got this little one right here. That's because Sly doesn't clear out its. So Sly keeps track of the number of recursive debugger levels you've entered. Like if I trigger the debugger, I can come back to the REPL while the debugger is running, and then I could in principle trigger yet another error, and this number will go up, the number of recursive errors you're in. But the thing is, it doesn't actually clear that until whatever you're evaluating actually returns. And because I'm running a nested REPL right now, even though I've gotten rid of the error, that counter is not going to go down again until my event loop closes. It's not going to go any higher than that, but it's going to stay at 1. So that's just telling you that I'm still inside of a nested REPL. That'll go away once I exit back to the top level. But yeah, so I now have a little server that I've got going on right over here, and just as before, I could do other asynchronous operations on this whole thing. I can set up intervals. I could launch multiple TCP servers running concurrently, all on this single threaded event loop. And there are a few other little things that I did when I wrote this. Is like I actually made a couple commands. I have a little echo. Are you mad at me for some reason? It gets mad at me for some reason.
It's okay, man. Live coding sometimes.
Event loop. There we go. Okay. Oh, it did actually send it back. It was just hung on something, and I don't know what it was. Let me just relaunch my little event loop down there. If I try and do anything on this right now, it's going to say end of file, and then just exit out of that. So where was I? Here we are. Launch the TCP server again. Cool. And then connect to that again. Now I can echo foo. Yeah. See? And right now, capital echo foo. Echo foo. Oh, I must be doing something stupid over here.
Wait.
Because it doesn't seem to be it seems to be broken on that specific command.
TCP/IP.
That's amusing. I wonder what that could be.
So
I didn't actually test that command after I reworked a little bit of this code over here. So I'm going to have to tinker with that a bit. This is just me screwing around last night.
I think you have to type in.
Clearly got it, but it didn't actually send it back properly, and I don't know why.
Hey Elijah, try quit on your command there, just because it's.
I can't send anything. This is.
It's gone now. Okay, got it.
It's not gone. It's just Sly refuses to let you type input if the underlying program isn't requesting a line.
Okay, got it.
And so I know that my client here, at least, isn't waiting for input from me. So it's probably blocked either writing a line to the server or reading a line from the server. And it's probably blocked reading a line from the server. Which means I probably need to, do something up here, and I don't know what it is.
Okay.
It clearly got to here. Actually, let me...
Yeah, that's probably better.
Since I have a logging library, I took the time to load in. I might as well use it. Echo command. Okay, and this thing's not coming back, so I'm just going to reset it. Socket client test. Echo. Boom. Yeah, it gets there. Here's the other thing. If I don't know what it's blocked on. That's just, oh. I know what it is. Right, socket data, socket, table string to octets, new line. I'm sure there's an easier way to do that. I just don't remember it offhand. The problem is that the command that I'm using on the client side is read line.
Yeah.
And the regex that I'm doing here is a single line regex, so it's not actually capturing the new line when it does that. And so this new message variable here isn't getting the new line, and so when it echoes it back, it's not echoing the new line back. And so this side just sort of sits here waiting for a new line it's never going to get. So there we go. And quit does work. If I quit, I notice, I actually get an end of file on the client side, and the server side exits. It returns something and gives me another prompt. That's how you know that it's exited properly.
Okay. Cool.
So yeah, and that actually exits the whole event loop. Anything else that's possibly running on this event loop is now dead, done, not doing anything anymore. That cleans up everything properly. This is sort of the alternative to doing things like free signal handler. If you don't want to keep track of all of the different little things you've got running in the background, you can just say, hey, no, exit event loop, and it'll clean up everything properly and exit safely.
Nice.
But yeah, so that's sort of the big stuff you can do with the library. You can make asynchronous web requests and get data back as byte arrays. You can run servers and just basically set a callback that gets called anytime data comes in from the client. And you can actually, when you do this write socket data back on the socket, you can actually also set the you can change what the read callback should be for any future messages that come in on that socket whenever you write socket data. And so I could actually say that once someone sent an echo command, I now want that socket to basically use some other processor, some other command processor for any future data, right? And you can actually do that, and that lets you have a different handler that you pass in at your sort of the top level of your server versus one that handles future requests from repeated connections or from still active connections, right? Like if you have a running connection like I was showing here, as opposed to connecting a new each time and sending and just doing a single transaction. So sort of the big stuff. Then there are a few other operations you have in the library. I'm sure I have it open here somewhere. If I don't, that seems rather silly, but it may be buried in my never-ending growth of tabs. Nope, I don't think I have it. CLAsync. What did I see? I do. I do still have the documentation. Switch to. Yeah. Okay. Is it this one? It is. It's this one. It's the first tab. Sigh. Okay. Then you have a few other things. You have they do have an SSL system, so you can actually make SSL connections. That's kind of broken right now, unfortunately, because it relies on another native library, and that other native library was recently either cl-async changed which native library it uses, or there was an update to that native library, and so for a lot of cases, it just mysteriously gives null pointer exceptions, which is just never something you want to see. But hopefully that'll get fixed soon enough, because otherwise it's actually pretty clean. I've used this before actually for doing some WebSocket work. It works pretty much the same way. You give a host and a port and a read callback, and and then you can write some data to the socket. And when a response comes back, it calls your read callback, and then you can deal with that new response data. You have pollers. This is one that I don't think is really useful from a Lisp side because it operates directly on file descriptors, and that's not something you generally have direct access to. But if you do happen to get a file descriptor back from like some C library, you can basically set up a handler, a callback to be triggered, basically whenever stuff becomes available on that file descriptor. Idlers, this is just lets you set up a callback to be triggered every time through the event loop. That's sort of the alternative to me basically saying update REPL every half a second. I could say instead update REPL literally every time through the event loop. I don't really want to do that because I feel like that'll burn my CPU, and there's not really any good point because I feel like cl-async is probably smarter about sort of sleeping and delaying when it doesn't have anything in the queue. And so if I have an idler running, that's just going to be active all the time, and I only really need this to be updating my REPL, slow in computer terms. And similar to a lot of the other things here, you have basically these free things that you can do. So you can free anything that you attach that sort of runs in the background. There's a corresponding free operation for it. Actually, the same thing with the TCP server. You also can you can explicitly free that TCP server instead of close TCP server. You can explicitly free the TCP server instead of calling exit event loop and just burning everything down. I would need to have some way of capturing this return value from the TCP server when I call that and storing that somewhere so that my handler could properly close down the server under a certain event. But that's certainly an option if you don't want to close down the entire event loop. You just want to close down that one server. Then probably the only a couple other things would be like you have notifiers. And this is how you integrate CL-async with multi-threaded library. And actually, I can demonstrate that right now. I should restart my event. And there we are. I can create a notifier. Let's make a notifier. Def parameter make notifier. Oh, right, yeah, sorry. Apparently my brain is kind of turning to mush. Make notifier. And this basically gives me a callback that gets triggered. Why am I bothering with the full name? Gives me a way to set up a callback that can be triggered from any thread. There's a flag I want to say single shot. And now I have a little notifier. And what I can do is from any other thread, this is basically the only place where multi-threading becomes a thing in this library, I can say cl-async, and this is also one of the only operations that you can do when you're not running inside of an event loop, is triggering a notifier. But I can trigger a notifier, and now every time I trigger that notifier, it's going to run something on my event loop thread, whatever callback I had set for that. And when I'm done with that notifier, like just about everything else in this library, I can free it. Free notifier. And now if I try and trigger it again, it says it's freed. It actually errors on the thread that tried to trigger the notifier instead of inside of my, event loop. But that's basically the only multi-threading sort of operation that you have in the library. But because it takes any lambda, you can close over some other communication channel if you need to be able to actually pass state back and forth. And actually, there's an example in here of somewhere of using it with L-parallel. That's in the threading thing here, of actually using notifiers with Bordeaux threads directly, or just with like L-parallel or something along those lines. Do they actually use No, they don't actually use L-parallel. But they do say like you could make a notifier that resolves a promise, for example, when some work gets done, and then you can use Blackbird to set up work to happen asynchronously based on when the promise gets resolved and that kind of stuff. This little example here is you give it some lambda to call on some background thread, and it'll run that on some background thread, catch the results, and then it'll use that to resolve a promise by triggering a notifier, storing in some local variable, and then that local variable gets used to resolve the promise. And then you can just say, hey, work on this lambda that'll happen on some background thread, and then you use Blackbird's ALET here to capture the resulting value asynchronously and do something with it when it comes in. And you can use L-parallel to actually spawn that stuff off and track the results and stuff like that. And that's really like all there is to cl-async in and of itself. It's actually it's not that crazy of a library. It's got a lot of networking stuff kind of baked into it, but otherwise it's more or less just it's an event loop. You can trigger events to happen. You can set up callbacks for those events. Not a whole lot more to it than that. Anyone have any questions? I realize I kind of sort of train wrecked through that whole thing, but
Thoughts?
I really need to just play around with this library. There seems to be quite a bit of things in here to understand. One thing I wanted to I was trying to understand was since you were bringing up the TCP server example, does cl-async not internally depend on usocket, or is it using something else?
It uses so libuv provides socket stuff.
Oh, okay, got it.
Yeah.
All right. Okay, so internally it's the C library. Got it.
Yep. Yeah, basically everything in cl-async is a wrapper around something in libuv.
Okay.
Libuv runs the actual event loop. Libuv does most of the stuff. Actually, if I break on my REPL here, you'll notice that I'm, halfway down, like, got all of these foreign functions running all over the place. Actually, no, that's not where I want to. If I break from inside of there, here we are. Yeah, now if I go down through here, you'll see, here we are. Lots of foreign function nonsense. Callback, wrapper, trampoline, all that kind of fun stuff. And then we get back into the, slink, REPL nonsense. And yeah. But the important bit here is callback, wrapper, trampoline, for an alien callback, and then we get back into SBCL, right? And this is the bit that's going on in in libuv, right? And just about everything going on in cl-async is really something going on inside of libuv. So libuv provides notifiers, libuv provides pollers, libuv provides a DNS system, libuv provides signal handling. Well, I don't know for certain libuv actually provides the signal handling. They may be using some really lightweight wrapper over notifiers to handle that. But the idea, it's the same basic idea though. I mean, it's just about all there's only like one or two places where they actually implement something, and most of the time they implement it by, here, how do I schedule something to happen on the event loop immediately, right? Like it just happens after whatever I'm doing now is done, or as soon as the event loop, resolves whatever work is already on it. Well, that's simple. You do a delay of 0. But because it's weird to think about saying delay of 0, they wrote a quick little utility in, I think it's events here, which is, nope, that's not where it was. Where was it? Is it signal handling? That seems silly. I know that it's in here somewhere. It's called wait, I think. Instead of delay. Clever naming. Was it wait? I think it was wait. Am I going insane? I may be going insane.
I didn't see a wait
Highly
in
possible.
the documentation.
Yep, I may be going insane. I remember there being a function specifically for this in there somewhere, but I don't seem to remember where it was.
Search the page.
It's not one page.
Oh.
Well,
anyway, point is really just that you can. I'm quite annoyed now that I can't find that. But anyway, there's really not one thing to be aware of. The documentation is a little out of date. They changed sort of the style here. A lot of the cases where you see an explicit argument for an event callback, that's now been changed to be a key argument. That's really the only big change that's happened since they last updated the documentation. I haven't noticed any other issues when I've been playing around with it recently. But pretty much across the board, anytime you see a positional argument for an event callback, that's become a key argument now. The event callback is just in case some weird condition happens or something exceptional happens on some object that's being tracked, like in this case by the socket, right? Like if an EOF occurs, for example, it calls the event callback with the information about what's happened in that exceptional situation. That's really all that is. There's also, for TCP Connect, it's got like a connect callback and a write callback. And this is, if you want to keep track of, if you want to do something after you know that the stream is connected, or or what is the write callback? After data written to the socket's buffer is flushed out of the socket, right? So if you want to, disconnect as soon as you know some data is sent properly, you can close the connection and a write callback, that sort of thing. I mean, for the most part, the documentation is actually fairly straightforward. There are just a few places where, they made some major change across the board, and then they didn't go through the documentation and actually update that. But it usually is relatively obvious what's happened and what exactly they changed. You just have to remember that they changed that across all the API. But yeah.
Cool.
Yep. It's a neat library. It's good if you need to do some network-heavy stuff asynchronously, I'd say. Much better than polling with usocket.
Very, very nice. Because I think we actually went through an example early on of writing like a usocket server. I know because I actually wrote it.
Yeah.
So this is a good thing for comparison to actually check out to see what the differences are. And for folks who are watching the stream, if you want that code, that is in the that should be in the Atlanta FP GitHub organization's repository.
Yeah, the usocket server.
Yeah, the usocket server
should be in there somewhere.
Yeah, and if you you can certainly look at that and look at this and see what the differences are. This looks a little simpler and much cleaner than the one that I came up with, but that one shows you how to use usockets properly too. So
yeah,
so yeah.
And usocket is nice if you just need something simple and quick.
Right.
Whereas CL-async gives you a lot. It's a bit heavier of a library because you're trying to manage, lots of concurrent stuff going on.
Right.
But I mean, it's neat that you could just set it all up so that all this is happening in real time, concurrently without having to spawn off multiple threads necessarily.
Yeah, and plus, since you're using libuv, you could interact with other programs on your system. In principle, yeah, I'm not encouraging it. I'm just merely saying that if you have some stuff that you want to interact with, you could totally do that since it's using libuv underneath.
Yep.
So,
yeah,
that's great. So thanks to Pavel and Elijah. I mean, this has been really great. I really want to try now. I have, like I said earlier, ideas for both cl-async as well as Flow, more of CLAflow, just because of some thoughts that we were talking about earlier. But join us next week. I will post an announcement on what we're planning on doing next week, hopefully on Discord as well as the Functional Programming Slack. But until next time, I'll see you guys later.
Okay, then.